So hello everyone. So thank you for watching this video. So this is Math 2526 class C1. So I split this course into three parts: part 1, part 2, part 3. So this is part 3 first class. You can regard that. So part 1 is about the population for statistics, about probability, right? So part 2 is one sample problem. So this is the first question in statistics. Then we move to other other problems, other statistical problem. So so today's topic is a two sample problem. Okay. So let's review one sample problem. Like if we one sample problem is just like we just have those data, one sample data. So from this data, we can do two things, right? First one, find confidence interval for population's average for mu. So we say this is the confidence interval actually for mu or for proportion. Okay. So this confidence interval for me is just like that. We know x bar sample means here. Then we believe population's average will be in this range, right? Okay. So the other thing is, but with this data, we can do hypothesis testing. We can test whether mu can be this number, or mu should be larger than this number or less than this number. So for those hypothesis testing, we just calculated as a test statistic. So we call this as just the cutoff point. Right? So we use as a formula. Cutoff point is here 0. So okay, the cutoff point. So instead, we just wanted to determine this distance is big, or we say this number like here, this number, the difference with 0 is big or small. So if this is big, then we will say HA, right? Mu and mu 0 not so close. Okay. So this test statistic. Sometimes we call this is z value, sometimes t value, meaning it's like check this cutoff point, check this number, big number, small number. We need t table, z table, or t table, right? So if z value, then check z table. The t value, check t table, right? So how can we determine this z value, t value? Just check this sigma, population sigma. If we know population sigma, then z. If we only know samples, standard deviation, we don't know sigma, then there's a t table, t, right? Okay. So and also like if we check a population proportion, usually it's z, because the sample size is quite big. So this is the one sample problem. Okay, so let's check out. So what is the two sample problem? So two sample problem is we have like a two group of data. Like we sample one data, sample two data, sample one data x1, x2, xn1, so y1, so y2, yn2. So we have those two group of data, or two samples data. So with those two sample data, which question we wanted to check? So the typical question is like this: is this one better than that one? So if we have two, we usually wanted to compare, right? Which one is better? Like, is this medicine better than that medicine, or is this treatment better than that treatment, like those, right? Like, is this a class? This class 1 perform better than class 2? So those kind of problem, we call this as a comparison. So actually, if we have more than one samples, we want to compare, right? If we have two methods, we want to check which method is better. If we have several methods, we also want to compare, and we want to determine which one is the best one, right? Okay, so we want to check out which one is better or the best. So this is a very common story, right? In many situations, we want to determine this, right? So how can we conduct those comparison? So the theoretical foundation is again essentially limit theorem or sampling distribution. Just this, x bar follows this normal. Okay, so this we say very, very important, because if we know something follow normal, then we can do many things. Like we can find probability, we can get some information. So here, so we can say like, so then x bar follows this normal, y bar follows this normal. So x bar is average for this sample, from this sample, y bar is average for that sample. So we have this, right? Okay, so normal x bar follow normal, y bar follow normal, then we have this result. So normal minus normal is normal. Normal plus normal is normal, right? So we have this result. This is a x bar minus y bar follow a normal distribution. So mean become mu1 minus mu2. Okay. But this standard deviation, we cannot use minus. Okay, mean can minus. So standard deviation, we cannot use this. We cannot use this. So why we cannot use this? So remember, this sigma is standard deviation means changement, right? So changement minus changement make no sense, because like for example, like if we say this, we have changement sigma 1, that one we have changement sigma 2. So if they're equal, then we get this, suppose this equals 0, then this means no changement. So this is very clear not true, right? So we say changement cannot be balanced. We cannot be changement cannot be cancelled out. Okay, so we say, so here we can say variance should be added them up. If x bar minus y bar, variance add them up. So this variance is sigma 1 square over n1, and this variance is sigma 2 square over n2. Okay, so this variance for x bar minus y bar. Okay. Okay, then here for normal distribution, we focus on standard deviation. So take a square root, becomes standard deviation. Okay, so this follow this normal. Then this one follow this, follow standard normal, right? From general normal to standard normal. So we denote this as z, right? So x bar minus y minus mu1 minus mu2, this minus the mean, this minus mean divided by sigma, this follows standard normal. Okay. Okay, so here for two sample problems, we just want to compare. So here HO is mu1 equal mu2, meaning there's two methods or two groups, no much difference, right? So we compare two groups, means we compare their average. Okay, so for HA, again, like we have just like one sample problem, we have three options, can be not equal, or more specifically, or larger than or less than. So here, which HA we should choose? So it depends on which what you wanted to say, or which one make more sense. So this determine HA, we need to judge from the problem itself, right? Okay, so now let's say that, so if the on the HO, we say if mu1 equal mu2, then mu1 minus mu2 equals 0. This part becomes 0. So we have this, right? This follow normal. Okay. Yeah. So if we know sigma 1, sigma 2, then we can find, we can calculate this value. So this is test statistic, right? So this is z value. Then this is so z value. So this is follow standard normal. So let's say like, okay, so suppose this is standard normal. So we have this cutoff point. See a test statistic. Then we can determine this number with 0 differ this number and 0 close or not so close, or this number is big number, small number. Like we can determine that. Then we can use this to make our decision. If this number quite close with 0, then we say HO, right? If not so close with 0, then HA. Okay? But the question is here, we don't know sigma 1, sigma 2. Right? Sigma 1, sigma 2 is population standard deviation. So we don't know them. So how can we solve such a problem? So just like one sample problem, right? We just replace them by samples standard deviation. So we replace them by S1, S2. So from sample, we can find sample mean, sample standard deviation. Okay? Okay, so now we replace sigma 1, sigma 2 by S1, S2, then we can find this test statistic. Okay, right? Yeah. So x bar minus y bar over square root of S1 square over N1, S2 square over N1. So we can calculate this number. Okay, so the question is, okay, like here, so we need to check this number is big number, small number. So the question is, how can we check this? So which table we should use? Z table or T table or other table? So here, so we have this problem like which table, or so we need to know those things follow which distribution. Follow which distribution. So such a question actually is a tough question. So exact distribution is so complicated. So we can only say those things roughly will close to a T distribution. So there's what for T distributions, what is degree of freedom? So the degree of freedom is also very complicated. So here we just pick so to make these things simple, like we just pick this degree of freedom. We just consider worst case. Let's say we say just check worst case. Okay, just like that. So here, what worst case meanings? So like here for two samples, we have 2 degree of freedom, n1 minus 1, right? So n minus 1 is the degree of freedom. So we have 2 degree of freedom, n1 minus 1, n2 minus 1. So we just pick a smaller one of them. So smaller one, this is worst case, because for sample size, we know sample size big, the better, right? So we just pick a smaller one, means the worst case. Okay. So then we have this cutoff point. Then we can use there's a t distribution. Okay, like a t distribution. So degree of freedom. Use this degree of freedom. Then we can determine this is big number or small number. Okay, so now let's consider this problem. Like so can we say class 1 performs significantly better than class 2 at this level? So here we have evidence like class 1. So x bar means like exam average. So suppose that we have the common exam for these 2 classes. So for class 1, average is 84. Class 2, average is 81. So from here we can say class 1 is better than class 2, perform better than class 2, right? But we need statistically check this, whether this difference is significant. So we just check this, right? We have evidence, but we need to check significance. So we convert such a problem as a testing problem. So here, this is a 2 sample problem, right? The class 1, class 2, we wanted to compare class 1 and class 2. So we have those data. The data is their exam scores. So we can here we just have their similar data. Like we have like for a sample, we have sample size in sample mean x bar and sample's standard deviation s. So we have this information. Okay, so for hypothesis HO is equal. So here mu1 stands for class 1, right? So mu2 for class 2. So this mu1, mu2 is so this x1 like 84 is the one exam's average. So mu1 we can regard as the average for class 1 for like so here is in this class we just wanted to prove wanted to say in this for this exam class 1 do bad. But can we say class 1 always do better than class 2? So just like that, So if this means like if this true, the means class 1 is significantly better than class 2. Okay, so mu1, mu2. So here means like always like if we have many exams. If class 1 always better than class always better than mu1 larger than mu2, then we can say class 1 always perform better than class 2. So we wanted to test that. So then calculate test statistic, right? So use this formula: x bar minus y bar. So s1 square over n1 plus s2 square over n2. So plug in here, we find, so x bar is 84, y by 81. So S1 is 7, yeah. S2 is 9, right? Yeah, 7, 9, and 25, 20. So 25, 20. Okay, so with some calculation, so we found this equal 1.22. Okay, so you can confirm this. So for those calculation, if you can use Excel, right? I also use Excel. Okay, so now we wanted to determine like this number is big number or small number. Okay, so here 0. Okay, so this we have cut point is 1.22. So we want to determine this 1.22 is a big number or small number, or the distance to 0. Like, or there's a distance to the for there's two numbers, 0 1.22 is close or not so close. So how can we judge this? So we can find critical value, critical value. So let's say this is, so let's check a critical value. So critical value means like we need to check, let's say we need to check a t distribution. So there's a degree if is 19, right? Okay, and so alpha is 0.05, alpha 0.05. So we just find that t star or t critical value, such that this part is 0.05. Okay, so we call this as this t star. Okay, a critical value. Okay, so check from the table, t table, so 1 tail 0.05, degree of freedom 19. So we found this number is 1.729. Okay, so now judge this number 1.22, big number, small number. We just use this as a standard, 1.729 as standard. So we found so like this 1.729 as standard. So here we say those numbers small number, okay, or those number big number, okay. So our number 1.22, so okay, 1.22 is here. So we can say 1.22 is a small number. So small number means their difference, like here, 84, 81. This difference is not so big, right? Not so big. So what is our decision? What is the decision? So decisions are class 1, class 2, class 1, class 2. Their performance quite the same. Oh, so to go back to the question. So can we say class 1 performs significantly better than class 2? We say no. Their performance we can regard quite similar. Okay? Or we can say this difference 84, 81 is not so significant. Okay? Okay, so this is our first example for two sample problem, right? So because we use t-table, so we will call such a problem as a two-sample t-test. Okay. Okay. So now let's consider problem 2. So here, this problem, we want to compare two proportions, like who is more popular, or who will win the election. Like we have two candidates. We want to predict who will win, or who is more popular. Okay, so we just do a survey. So let's say, so as we have this result. For candidate A, we check among 1,000 voters, we find 420 will vote for him, or 420 like this guy. So we have this. We say percentage of proportion for candidate A is thus. Right? So that's equal. We say 42% people like this guy. Right? So for B, it says, so for B, so percentage for B, so P hat means samples percentage, right? Yeah. Okay. So for B is 900, 2,000. So this equal 45%, right? Okay. So from our data or from our survey, we find candidate B has 3% more percent than candidate A, right? So like their popularity is 45 versus 42%. So we have evidence that B is more popular. But the question is, this evidence is strong enough? So can we say he is more popular in general? Like from sample, we can say that he is popular. But for population, can we say he is more popular? Right? Okay, so we convert such a problem as a testing problem. So HO is P1 equal P2. Quite the same, not so popular. And HA is P2 larger than P1. So here P2 just PB, right? P1 means PA. So PB like P2, P1 less than P2 means P2 is more popular. Candidate B is more popular. So this is a two-sample problem. Okay. So for test statistic, we just use this. So x bar minus y bar over s1 square n1 plus s2 square or n2, right? But this test statistic, I put this as z equals z value. So why this is z value? Because sample size is quite big, right? So when sample size is quite big, T table, Z table, no difference. So we use Z table or Z value. Okay, so here X bar is just the P1 hat, 42%. So because this is 10 data, right? 10 data. So data is like, okay, so 1 plus, this 1, this 0, this 1, this guy say yes, this guy say no. So then divide by totally 1,000, right? So this is just the percentage, like how many say yes, divided by total, right? So this X bar is 42, I bar is 45. Then for this 10 distribution, we know its variance sigma square variance or S square equal, so here variance equal PQ. So S square equal P hat Q hat, variance sigma square equal PQ, right? So 1 0 distribution sigma square PQ. So S equal P hat Q hat. So S1 square, we can say P hat 42 times Q hat is 1 minus P. So 58, right? So divided by A. So here P2 hat is 45 times 55 over 2000. Okay, so we found this number is 1.57. So this is Z value, so we can find the exact P value actually. So what is P value? So P value just like that. Okay, so here negative 1.57. So P value is this part. So HA is less than, yeah. So P, this part is a P value, also this part. So from the from the Z table, we can find this P value. We find, let's say, P value equal 0.00582. Okay, so then we compare P value with alpha. So what is alpha? So let's check what is alpha. Oh, so here no alpha. The problem do not specify this alpha. The questions like we have the data, so can we say candidate B is more popular? So if the problem do not give us alpha, then we say we will pick alpha as 0.005. So we say by default is alpha, we will pick this. Okay, so we find this P value is a little bit larger than alpha, right? So what is your decision? Decision is this distance is not so big, or we still can believe there's two numbers quite close, or we can say the difference is not so significant. So our decision is we will, from HA, HO, we will believe we will pick HO. So HO says like the popularity is quite the same. Then we'll go back to the question, can we say he's more popular? We say no. We cannot say candidate B is more popular than candidate A. So even though our data suggests this, right? So the story part is the same. So data have some evidence, but we say, oh, your evidence is not so strong. So for your decision, I don't like HO, HA. You just should tell other people. We say that your decisions, we cannot say he is more popular, right? Okay. Or for election, if this is for election, so we cannot predict he will win, right? We still need more information. We still need to wait. Okay. Okay. So now let's check this example 3. So this is again is a two sample problem. We have a company A, company B. We want to compare them. So compare them based on this data. So this data is we just check compare the customer certification level of these two companies. So we do a survey. We ask ask 174 customers for company A and 355 for company B, and there's this certification level is from 1 to 5. Okay, so we just ask customer to pick one, like 1, 2, 1, 2, 3, like 4, 5. So 5 means the best. 1 means so so we ask the customers what is you feel your level for their service. So some people pick 4, some people pick 5, some people pick 2, right? So we just use average. So x by 3.51 for company A and 3.24 for company B. So S is standard deviation is this. Okay. So here, what we wanted to say is also HO always equal. So what is HA? HO is the level quite the same. Like 3.51 and 3.24 quite the same. So what is HA? So HA, let's see. So HA is actually up to us. We can say like maybe like HA. So here we may, so if we wanted to, so here if you wanted to say like company A's certification level is higher than company B's certification level, which has used HA like this. And HA, so maybe sometime you can do this, right? Okay, mu1 not equal mu2. There's two, their certification level, just simply say not equal. So equal, not equal. So here we say put HA, this one is also, it seems okay, right? This one okay. Then we just pick the ones that make more sense. So here, this larger than this means this is better than this. So they are equal or not equal, maybe those things we do not have much interest, right? So the more interesting thing question is this is better, this company is better than that company, right? Yeah. Okay, so now we want to calculate the test statistic. So uses the formula x bar minus y by s1 square n1 is 2 square n2. Just plug in here, right? Okay, so we get this number. Okay, so then this t value or z value. Like, okay, so we have this number. So here's 0. So this number is 5.684. So we want to judge this 5.684 is big number or small number. So we need to check some tables, a Z table, T table. So here we say this we say Z value, T value doesn't matter. Z table, T table doesn't matter because sample size quite big, right? N1, let's say, source number N1 is 174, so this big number. Yeah, and 1.355 was quite big. So we can use a Z table is okay, a T table is okay. Okay, and also like from this number we say either Z table, T table, we know there's a 5.6. This number is so huge number, right? So for normal distribution, for standard normal, we say like 1, 2, 3. We say we have this 1, 2, 3. Above 3 is so. For standard normal, says 3 is a big number because let's say we have this rule 1 sigma 68, 2 sigma 95, and 9.7. So outside the 3 almost only the 0.003%, right? So 3 is a big number, 4 is a big number. For T table is also like that. So this number is quite big. So without checking T table, Z table, we can make what decision. We can say the p value should be very, very small. P value can be like this. Okay, and the decision is HA. So we can say the data. This p value very, very, very small, meaning the data is very, very, very strongly. We can support this company A, so certification level is higher than that company B's certification level. Okay. Okay. So this class is the material. This class is a two sample problem. Okay, so we can have a 2 sample T test or 2 sample Z test. So the T test means we need to check a T table. Z test like this one, Z test, Z table. So 2 sample Z test, 2 sample T test. So this is a 2 sample problem. Okay, so we say 2 sample problem is quite the same as 1 sample problem. Only this difference is, let's say, just the formula to find the test statistic. Okay, so there's a formula: x bar minus y bar over s1 square over n1 and 2 square over n2. Okay, use this formula to find the test statistic. Okay, so we can stop this class. Okay, so and see you next class. Okay, so thank you for watching.